I'm Dr. Courtney with the Quantitative Reasoning Center. Majoring in science or engineering is a challenging thing. And I can remember when I was a first and second year student in college, there were many occasions when I wanted to change my major to something else where I simply wouldn't need to take as many math courses. And that video of the tiger at Louisiana State University at the beginning of this clip was very important to me because it reminds me of a song called Eye of the Tiger. And the idea in that song is that I would not waver, I would not falter, I would not fail. I was going to succeed in what I set out to do. See, I come from a Hispanic family where nobody had graduated, no one before me had succeeded in a science or engineering major, and I watched uncle after uncle and cousin after cousin either return home from LSU after having flunked out completely or having changed their major away from the science or engineering discipline that they had intended to pursue originally. Okay, we're having a look at 13.3 number 15, and we've changed the numbers just a little bit, but the procedure we're going to demonstrate here is the same as the procedure you need to follow, but you need to change the numbers when you work it for homework back to the numbers that are in the book. So we're starting at a point 0, 0, 3, moving 10 units along this curve and wondering where we end up after that happens. So let's think about the idea problem solving format, because we need to identify the big principle here. And the big principle is arc length, because we're moving along a curve a certain distance and we're moving 10 units along that curve. So we need to figure out where we are, at what point on that curve is the arc length 10 units from the beginning. So we want to use arc length to find position. And as we develop our plan, we want to draw a picture, and the computer algebra system, MATLAB, Mathematica, and a Calc tool 3 will also do it, will graph this for you. And if you don't recognize it immediately, it might be a good idea to graph it. But this curve is a helix, and it's a helix of radius 3 centered about the y-axis. So as we draw a picture to see what's going on, we make this the x-axis, this the y-axis, and this the z-axis. And we're starting at 0, 0, 3, so that's this point here, and essentially this helix is winding around the y-axis, so we need to have some arc length s, and this is our unknown point where we end up, and this is where the arc length ends up to be 10 units. So let's go ahead and develop our plan now that we have our picture. So we need to express arc length in terms of t final. And t final is the time or the parameter value at which we've gone 10 units. But that's like an unknown at this point. Rather than saying, how far have you gone at t equals 17 or whatever it might turn out to be, we're finding what is the value t after you've gone 10 units along the curve. So we solve for t final, and then we use that t final to compute, and let's call it r final, which is the position at arc length equals 10. So this is where the arc length is 10 units, and let's call this moment in time, or this parameter value, t final. Alright, so let's begin to evaluate this, and we can recall the arc length formula. Well, to know how far you've gone, essentially you want to integrate the speed along the curve from the beginning point, t equals 0, because it says we're starting and the start instant is t equals 0, to t final. And here we need to have the speed dt. And so let's have a little aside where we think about what the speed is, and we could just look up the arc length formula directly in the book. But thinking about it as the speed helps us remember where it came from. The speed is equal to the magnitude of the velocity vector, and the velocity vector is the rate of change of the position vector with respect to the parameter. Now, it's not really time when we're just parameterizing math problems, but you can usually think about it as time. And in a lot of physics and trajectory problems, it actually is the time. So, what is dr dt? Well, it's the derivative of the x component with respect to time, and the derivative of 3 sine theta is the derivative of 3 sine t is 3 cosine t. The derivative of 4t is 4, and the derivative of 3 cos t is negative 3 sine t. So this is the velocity vector, and now we need to compute the speed as the magnitude of the velocity vector. So if you recall, that's the magnitude of the x component squared plus the magnitude of the y component squared plus the magnitude of the z component squared. And when you square a negative number, you get the positive number. And here, something interesting happens because we have a 9 cos squared t and a 9 sine squared t, and we can use the trig identity, sine squared t plus cosine squared t equals 1. So this simplifies because we can, let's go ahead and take a couple of steps. We have 9 times cos squared t plus sine squared t, just combining these terms, factoring out the 9, plus 16. Now all this is equal to 1, so it's just the square root of 9 plus 16, or the square root of 25, or 5. So the speed of the trajectory is 5 units per second, or units of length per unit time. We're really not told that our time unit is in seconds, but we can move forward with this. So S is equal to the integral of 5 dt from 0 to t final. So it's 5 times t final. And we're told that we end up 10 units downstream. So t final is simply equal to 2. Alright, so we know now that at t equals 2, we've moved 10 units along the helix, and now all we need to do is figure out, once you move, well, at t equals 2, where are we? So r at 2 is equal to 3 times the sine of 2, 4 times 2, which you could simplify to 8, and 3 times the cosine of 2. So this is the answer. This is our final position. And let's think about how we might assess this. How do we think about whether or not it makes sense? Well, the most reasonable way to do it would be to graph it, and graphing would give lots of insight. But another way that you could think about doing it is, as you're moving along the helix, you know that a lower bound of the distance that you travel is going to be given by how much you went if you were only going in a circle without moving in the other direction at the same time. So we have a circle of radius 3, and the arc length along that circle is simply equal to the radius of the circle times the angle. But in this case, the angle is the same as the parameter t, so the arc length would be the radius, which is 3, times the time, which is 2, and that would be 6. And we can also think about how much we moved in this direction. Well, if you think about how much we moved in that direction, the distance that we've gone is 8 because that's the y direction. And these coordinates are orthogonal to each other, so the total arc length would be the square root of 6 squared plus 8 squared, which is 10. So this is a very simple assessment. It happens to give the exact number, but it tells us at least that we're not completely nonsense in the position we ended up at.